Today, we'll be discussing how to build a modern search engine that is both fast and performant. We'll start by providing an architecture diagram for this modern search engine, and then we'll spend the rest of the presentation focusing on a deep dive of BM25s, which is a very recent paper that has introduced a new traditional search algorithm that can be up to 40 times faster than, for example, an Elasticsearch implementation today. So let's start by going through a diagram. Now, when we're planning out this modern search engine, we need to be able to leverage the benefits of the more recent vector-based search, which can understand this semantic meaning, enabling users to, in natural language, get the most relevant documents to them, so this fuzzy matching, as well as traditional keyword-based search. So sometimes users will know exactly what they want, and we want to be able to return results that match this with the keywords and with their filters. So our system needs to be able to leverage both of these benefits and in turn accommodate for the weaknesses of each of these individual strategies, and ultimately as well, it has to be fast. So let's start with the flow. We have a user here, and we need to get this query, which is in natural language, as well as a set of filters. So this can be, for example, genre or color or category, whatever the filters that you would typically use via drop-downs or selectors for your product. This is what that is representing, and the query is what they'd be putting in the search bar. Now I have this optional LLM module here because one way that you might want to approach helping your user generate a search is actually via a conversational setting with an agent that you have designed. So via this conversation, you can build out using the LLM what filters that you want to provide as well as the query, and then trigger this search for them. That's an optional step that can provide quite a good experience, but in general, we just need to get these queries and filters. So if you're implementing this today, this would typically be directly provided by the user interacting with your website. Now we're going to speak about semantic and traditional search. Let's start with the semantic search first. Now, this semantic search, what we're representing here, is typically provided by a vector database and a full search over that, or using some type of algorithm, for example, a hierarchical navigable small world, which is what I have in this diagram here reflected. Effectively, what this does is it takes all of your documents and it generates an embedding for them, which represents the semantic meaning. It's a numerical form. It stores this in an index, which has a search algorithm over it, enabling you to, at query time, take the user's input, make an embedding for that, and then compare semantically by calculating a similarity metric between the user's query and all of your existing documents, which are the most relevant results. And assuming you have a good indexing algorithm over this, then it can be extremely fast. One thing though that you need to answer is if we're introducing filters to this as well, like I mentioned before, genre, category, location, you need to find a way to add this into that flow. There are two main ways. You can do it pre or post search. Effectively, if we do it post filter, what this means is we do the semantic search over all of your documents, over all of your data, and then after that, we apply the filters. This has limitations because it now becomes very difficult to determine how many results you're likely going to have at the end. So for example, if you want to return the 20 results, the 20 best results, if you do the filtering after, at the worst case, it's possible that you might even have 0 results. But in general, you could have arbitrary number of results because the semantic search is going to return some set of documents and you don't know if those are going to match the original filters. So an alternative that doesn't have that problem is pre-filtered search. This means that we apply the filter information before to the documents, removing them from the future search, and then perform the semantic search over that. Now, if this isn't implemented well, it can have significant performance implications because if we just did that filtering out before, it is typically going to be the case, and unless you do something otherwise, that you will break the indexing algorithm that has enabled you to do the fast search over it, and instead you're going to have to fall back to a brute force approach, which means calculating the similarity between every individual document and the query all at the same time, and then returning your results. That can be slow, especially if we're talking millions plus of documents that you need to search over. So what you should look to do instead is an idea of single stage or performant pre-filtering. Depending on which vector DB you use, they'll have different names for it, or if you implement it yourself. And if you want to know more about that, we can do a deep dive on it in another presentation, or you can refer to articles on their websites. But as a teaser for how you might approach that is by, for example, including additional metadata that you can then build up an allow list, which effectively says when we're doing this search, it's checking as well whether it's in the allow list, which is based on the filters. Again, this should be a full presentation, so if that's something you're interested in, let me know and we can dive deeper into that. Okay, but effectively, let's say we have this performant pre-filter search going on. What we are going to get as the result of this is a set of semantic candidates. So this is that fuzzy matching based on the user's query in natural language. Which of our documents do we think are the best match for that? Now, let's talk about our traditional search arm. So in traditional search, what we'll typically do is we'll take our filters and we'll do some keyword-based searching as well. And the main way that this is done, for example, if you're in a commercial setting, you quite often will be using Elasticsearch, and they'll use an algorithm called BM25. What we'll be focusing on for later half of this presentation is BM25s, which is a very recent paper that's introduced a new implementation strategy for BM25 that is significantly faster. And it needs to be significantly faster for an architecture like this because, as you can see, we're trying to do two systems and we're doing them in parallel. So the ultimate wait time that we have to for this component of the search engine is going to be what is ever the slower of the semantic or the traditional search. So ideally, we want them both to be fast. But anyway, after we do this traditional search, we'll have our traditional candidates. We can now group these together in a candidate pool. So let's say that we've had M results from our semantic search and we've had N results from our traditional search. We now have this M plus N candidate pool, but we want to return just a subset of that. We want to return just K. So what we introduce now is a re-ranker module, and this is something that is getting more popular. So for example, Cohere offers an API endpoint for this, where the purpose of this re-ranker module, it might use an LLM, or it might use more traditional machine learning techniques, or it could use very naive approaches, is we take this candidate pool and we ask ourselves again, based on the query, which of these do we think is most relevant to the original query? So one way, for example, how Cohere is doing it is you fine-tune an LLM to do exactly this task. Ultimately, though, the output of this re-ranker module will be your top K results. And we can then return this to the user as the result of the search. So that's the high-level structure. Let's recap to go through it again. So we're going to start by the user somehow providing us with a set of filters as well as their query. And then we're going to execute two arms in parallel. We're going to execute our semantic search, which is going to give this our fuzzy results, our semantic results. And we're going to execute our traditional search, which is going to give us keyword-based results, scored high for things that are more relevant based on that. We're going to then get our candidate pool. We're going to provide this to a re-ranker module, which is ultimately going to filter it down and return just our top K results for the user. So as you can see, this is actually quite a scalable and quite a modifiable approach as well. You can tweak different elements in each of these modules. But one thing that you will need no matter what is for both of these arms that you're executing in parallel, to be fast, especially if you're dealing with a large user base and you still want to provide a good UX. That motivates why we're going to focus on BM25s today, as it is a way to significantly speed up your traditional search. Why, again, this is relevant is, let's say that we have the total time it takes for this engine to execute, and we have the total time that it takes for your current search process to execute. Now, in this new version, what we're introducing is a re-ranker module, so that's definitely going to add additional time to your search. But if we can make the parallel arms, the traditional search or the semantic search, shorter, then it's possible that the re-ranker module plus your other introduced search will have a total time that is the same as your existing search algorithm, or potentially faster, depending on how performant your current implementation is, but ultimately is going to have significantly better performance. So let's say we're not increasing speed, but we're increasing the quality of results. Then it's quite likely that this is going to translate into a better experience for your user and associated down funnel metrics. So with that overview, with that motivation, let's now move into the deep dive on BM25s. Let's start with why you should care. And I think I've alluded to already the main reasons why you should care about BM25s, but just to highlight again, the most important is that it's fast. Benchmarked on multiple datasets, this paper found that at some points it's over 45 times faster than what is implemented currently in Elasticsearch. That is a significant improvement that has practical benefits for your user base, for your product. Now, This is also a very practical approach. So BM25s is actually being implemented in Python with only two integral dependencies, that being SciPy and NumPy. What this means is the memory footprint can be kept quite low as well. And so it's suitable for edge deployments or just in general, if you have low resource environments, this is a good solution for that there as well. Now let's start talking a bit more about why it's so fast, and we'll speak more about all of these details in the later presentation. So this is more of a precursor to that. Firstly, it builds on some interesting insights. So it enables eager index time scoring. Now, if we go through the BM25 algorithm, which we will later, we'll notice that under some assumptions, the vast majority of scores are going to be 0, or we're going to be able to calculate them in advance. And by doing this process at index time, it then means at inference time, so when your user is actually doing the search, we can make this process very fast by only requiring a few operations. As an extension of this is that sparsity. So what I mentioned is a lot of the scores are going to be 0 in general. That implies that we're going to have a sparse index. And if we leverage that knowledge, then we can use better data structures so that we can efficiently and performantly perform operations over this sparse index. And this last one is more of a practical consideration that you need to be aware of if we were to use BM25s. And that is that the default implementation returns a partition. So an unordered selection of k results that are most relevant to the query. That means that they're not filtered in order of what is the best match. It's just you're getting that collection. By doing that, it means that we can apply selection algorithms that have on average linear time complexity, as opposed to if we were to require the ordering as well, that would make us require logarithmic. As you remember from the diagram for our overall modern search engine, this doesn't matter for us for our use case because we will be providing to the re-ranker module, which will do the ordering. So for our use case here, having just this partition has no impact for us, and it's actually beneficial because we can do it faster. But if you want to do the ordering for your specific use case, you will need to apply that on top, and it will increase the total complexity, time complexity of your system. Let's focus on the results here. So I mentioned it's faster. Let's actually see that. This is taken directly from the paper. Let's focus on BM25s, so which is what the paper introduces, and the Elasticsearch benchmark, which is ES here. Now, if you look through these results, you'll see that the BM25 is strictly more performant than Elasticsearch. And for some of these, it's up to 45 times a improvement. What these numbers are telling us is the amount of queries per second that can be provided by both of these systems. So larger queries per second is better. It means a more performant, a faster system. So as you can see, it's quite a diverse set of data that this has been tested on as well. So you can be relatively confident that, that this is going to be more performant for your specific data set as well. But again, always benchmark, always test yourself. So now we have that information, let's actually talk about the BM25 formula. To understand BM25s and how it improves and how it gets that speed advantage, you need to have an understanding of BM25. Thankfully, it's a relatively simple algorithm, so we'll go through this today, or a simple formula. Firstly, some notes on the naming to, I guess, demystify that. The BM is best match, and 25 is it's just the 25th iteration of effectively trying to come up with the best algorithm for doing this process. So nothing really technical implied by the name. It's just a very straightforward explanation. And again, if we go through the formula, I think we can step it out quite simply as well. So this is the base of the BM25 algorithm. Let's have B represent our score. And what we're saying here is we're taking two arguments. We're taking in the query, which we're calling a capital Q, and a document, which we're taking D. So for this example, we're calculating the score for a specific document given a specific query. How we calculate that score is, let's say we have some scoring algorithm, which is represented by S here, and we summate the result of that scoring algorithm for every individual token of our query. So I'm using lowercase q here to indicate a token, a subcomponent of the broader query, which is the capital Q. And we sum it obviously for all of the tokens in the query. So that's a high level structure. Let's now dive into what that actual scoring algorithm looks like. So if you've looked at TF-IDF before, which is a very common introductory machine learning algorithm that you'll learn about, you see it basically is just an extension upon that, where we introduce this new term, which you can see here on the denominator, this curly D. Before we go into that though, let's just do a refresher on TF-IDF in case you haven't come across it before. Let's start with TF. This stands for term frequency, and it tells you the frequency of the token in the document. And your intuition here is that if a document is going to be more relevant, so that means we should assign a higher score, then it should have the keyword that we're looking for, the token, as more frequent in that document. Inverse document frequency is the IDF part, and that tells you the uniqueness of that token across all of the documents. And again, your intuition here is that if a token is very common across all of the documents, then it's going to be less good at demarcating or identifying a specifically relevant document. So the exact example, a common example that we would give here are filler words like the or a. That's going to be in most documents. So actually using them to assign higher relevance to your specific document is not a great idea. Now that's the classic TF-IDF approach, but there are some weaknesses here. Firstly, there is no, penalty for term frequency or diminishing returns for term frequency. And that means we can do things like keyword stuffing. If you just put a lot of the keyword in the document, then the scoring algorithm with just TF-IDF is going to continue to provide a higher score, holding everything else constant, which is probably not exactly what you want. The difference between including a term 1 and 5 times should be different between if it's been included 100 and 105 times. And then the other issue is there's no penalty for long documents. Now, if we have a long document, then it can be quite possible that we're going to have more of the token, but it might not necessarily be as relevant to the original user's query because it could include a lot of other information. So BM25 is motivated by trying to address those two issues. We want to provide diminishing returns to the term frequency. We also want to penalize the long documents. This is where that curly D comes into play. And let's go through basically how that works. So this is what that curly D represents. It's the term frequency plus these two parameters, these hyperparameters here. We have K1 and B. And then in the brackets here, you have this other new term that we've introduced. So we have the cardinality of D. So that's the length of the document itself divided by L average. So this L subscript average is just the average length of documents in your total corpus. And we'll consider this total corpus, this whole set of documents, as capital C. So let's first focus on that penalization for longer documents. As you can see here directly, we've incorporated this penalization here with this final term here, where we have the length of the document over the average length. So if we increase the document and it's a lot larger than your average length, this term is going to be larger. This is in the denominator. This is going to ultimately reduce the total score. So we have that penalty. I feel like that's quite intuitive to see how this could come into play. Let's now think about how we can get that diminishing return to the term frequency. This is perhaps less intuitive just by looking directly at the diagram, but if you were to take the partial derivative of this equation with respect to the term frequency, what you would get is actually a fraction, and it'll be a result that is strictly positive, and there would be only one instance of the term frequency component, and that would be in a quadratic term on the denominator. So what does this imply? This implies that increasing term frequency is going to have a increasing impact on the ultimate score, holding everything else constant. But again, because that term frequency is on the denominator, it is going to have a decreasing or a diminishing return as we increase term frequency. Because as we're increasing the term frequency, our denominator is growing. So our partial impact is still going to be strictly positive. So it's always increasing, but that is going to be a smaller and smaller partial contribution as we increase term frequency. So effectively then, what that implies is we have exactly what we want. We have that diminishing return to term frequency. So again, to recap what this algorithm is and the core components, we have our traditional TF-IDF, but we address two weaknesses. That is, we add diminishing returns for term frequency, and we have penalization for longer documents. We do this via the introduction of this curly D term. K and B are hyperparameters. These are set in advance. And again, this is where you can think of that iteration. This is the 25th try of it. This setting has been done basically based on trial and error. And if you're doing this in an application, you would do trial and error effectively to determine K and B. Common scores are, for example, 1.5 and 0.75. So these are small decimal values. Okay, so that's the high level overview of BM25. Now let's start focusing on how we transition this into the implementation that is BM25s that you see in the paper. Firstly, let's try and intuit some cases here. The first case that we should intuit is what happens if the query doesn't occur at all in the document. In this case, the term frequency is going to be 0, which is going to mean that the whole score collapses to 0. As you can see here, it's multiplied together. So if one of them is 0, it's going to collapse, and the ultimate score is going to be 0. So this means that ahead of time, we can know if this token does not exist in the document, then the score for that token is obviously going to be 0. That's quite intuitive, I think. So if we transition this into thinking about how we can make this work at index time, what we can do is as follows. We can define a vocabulary, which can just be based on all the tokens from all of your documents. And then we can say for each of these documents and for each of the values, each of the tokens in our vocabulary, do they occur in the document? If they don't occur in the document, we automatically can assign the score as 0. And that means that we're going to have basically part of the equation already calculated. And then additionally, if for the document the value is not 0, so the term does appear in there, what we can do is we can ahead of time calculate the score for that token. That means then that we can build up an index which has dimensions based on the vocabulary and the number of documents, and we can have preset scores in there. So it's eager scores. These scores won't represent the full BM25 because what we have to do is still do that summation element that you can see here from the outer argument, which means we still need to know the query at inference time, but everything else we can do beforehand at index time, which means when we're actually using this at production, the user comes along and they provide your query, we can change this to a process that basically only involves slicing or indexing, or I guess filtering into our index to not use too many terms of index, and then summating over the individual scores that we've eagerly calculated. That means we can do this whole process really fast. Let's make it more concrete. Let's show how we would do this at inference time. So we're going to talk about how we can assign scores now. Let's step through it. So we have this matrix. We can think of it as our index before, and it's got the number of rows equal to the vocabulary, the length of the vocabulary. And so each row in here is going to be a token, an element from our vocabulary. And the number of columns is equal to the number of documents that we have that we can search over. So each column in this matrix effectively represents one of our documents. Now, let's say the user comes along. So we're at inference time now, and it provides a query. So again, this is this capital Q, and this query represents a whole bunch of sub-tokens. And what we can do is we can then filter out from the vocabulary these rows that represent or correspond to the subtokens from the user's query. So as you can see here, we end up with a smaller matrix where now we have the dimension for the number of rows as being the length of the query. Okay, so we're already looking quite close now. We then have to go to the process, the final part, which is the summation of calculating the score for the query over each document. We can again do this quite simply. So if we have on each of the rows here the scores for effectively each of the document for the specific token. So for example, in a single cell, you would have the score for that token from the query on that document from your corpus. And then that means that if we were to sum all of the values in the column, we would get the total value of the query, the total score of the query for that document. So we can do exactly that. We sum over each column here, and again, each column is the documents, and we'll get a single vector as a result. And each entry in this vector now will have the score, the BM25 score, for that query from the user on that document. So dimensions here, we have one row. That's all that we need now. This is the total score for the query. And then for each column, we have all of the documents from our data set. So that's great. That's basically all we need to do. That's the calculation. And you can see it's kind of just turned into a process of filtering an index and then just doing a summation over it. So minimal operations, and we can do that really fast. What we though still need to do is return that top K partition. And all that requires now is applying that selection algorithm to this vector, or you can think of it as an array of scores. So effectively, we find the partition that has our top K scores, and then because each of these columns represent a document, we in turn also have the most relevant documents. So we have the most relevant documents now, and we have their scores. We can return this now as our traditional candidates in that broader modern search engine that I motivated at the start. Okay, so that's an overview of effectively how we do that calculation. Let's just recap it one last time. So we start with this eagerly populated matrix of scores that has number of rows equal to your vocabulary and number of columns equal to the number of documents that you have to search over. A user provides their query, which we tokenize to get subtokens. And then we use these subtokens to filter out the original matrix. And then we summate over each of the columns, which represent each of the documents, to get the total BM25 score for each document. We then do a selection algorithm to get a partition of the top K scoring documents. That's primarily how we do this implementation for BM25s. Let's talk more about now sparsity and how we'll actually technically implement this. So if you were to look along at the code of how this is actually implemented, you can follow more closely. Firstly, before we go through there, remember that this original matrix is sparse. So that means that a lot of the scores are going to be 0. And that's all the cases where a term from your vocabulary wasn't in the document. Now, because of this, we can leverage data structures that are more suited to sparse matrices. And what we're going to focus on here is compressed sparse column format. There is also compressed sparse row and a few other variants to do it. We're focusing on column. This is what's motivated in the paper, but you can effectively think of row as being a transverse of this version. So let's start. We have our dense matrix. So this is just the overall form. And you can see here that it's sparse. There are a lot of 0 values here. This is what we're referring to when we're talking about sparsity. Sparsity being the presence of multiple zeros in the data set. And if we're thinking about this practically, it is likely that this matrix would be huge for your organization, for the search over all of your documents or over all of your products. And it's also very likely that it is going to be extremely sparse. There are going to be a lot of terms that a user could query that are not going to be in that specific document. So that motivates us trying to find a way to more efficiently store this and more efficiently perform operations over it. That leads us to the compressed sparse column format. This effectively is going to leverage 3 arrays. We have a data, an indice array, and we have the pointer array. These combined provide us a way to both store the dense matrix in a more compressed format, as well as perform operations, in this case over columns, extremely efficiently. Let's start with the data array because it's most intuitive. We effectively fill this array with all of the non-zero values from the dense matrix. So if you see here, again, in column format, what we do is we start from the leftmost column from the top and go down, then move on by shifting right one. So we go 5, 11, 1, that's the first column, then 2, 3, and then 8, 1, 3. So we're just filling out this data array with all of the non-zero values. What we can then build out is our indice array. This maps directly to the data array. And what this is telling you is for the element in the data array, what is its row position, its row coordinate in the original dense matrix or in a dense matrix representation. So if you can see here, we are representing the value 8. And if we look in our dense matrix, we can see that is in the first row. So using 0 indexing, the value there is 0. So in our indice array, we provide the value for the row there as 0. Let's look at another example. Let's look at the value 11. So in the first column, we can see that this is in position 1, 2, 3, 4. Again, using 0 indexing, this is row 3. And you can see here in our indice array and our data array, 11 and 3 are mapped together. So again, quite intuitive. The element of this compressed sparse column that requires a little bit more thinking to just wrap your head around about how they all connect to each other is this pointer array. The pointer array is effectively going to map the data array to columns. So what we're using this for is to tell us basically when does a new column start, and we index in that based on the data array. Let's make it more concrete here. So a first example is quite simple. We look at our dense matrix, and let's say when is the first non-zero value from our data array in the dense matrix. So here we can see in the first column. So here we have 5. being the first non-zero value in the original column, and that is having element 0 of the data array. So we're doing a pointer here, we're storing the pointer 0 to the data array, which represents the first column. Let's now look at how we can do the next element. So what we want here is to find the position for the first non-zero value in the second column. If we look at our dense matrix, we can see this is the value 2 here. So now we look to our data array. What is the position of the value 2 in our data array? And again, using 0 indexing, this is the value 3. So we store the pointer of 3 in our pointer array, which references the data array. And we do the same process for the other ones. What you will also notice here, or what's important to notice, is the length of this pointer array is always going to be 1 more than the number of columns in your original dense matrix or in the dense matrix representation. So for example here, this is why we see that we have this last element here for 8, which is the final result. So it's not actually for a column here. This is the last one that would play into the pointer array. Why do we do all this? What is the benefit? Firstly, like I mentioned, we can store this in a significantly compressed format. But secondly, this format enables us to summate over columns or perform operations over columns extremely fast. So let's say that I want to add up all of the values in the first column. I would go in my index pointer array and I would take the starting position and the position 1 next, and I would get 0 and 3. So this would then give me pointers into the data array and would tell me effectively sum everything from element 0 to 3 exclusive to get the values from the first column. So in this case, it would give me 5 plus 11 plus 1, which is exactly what I want for this first column. So it's given me a really efficient way to do so. Let's give another example here. So let's say that I want to get all the values in the second column. Again, I go to my pointer array. I see I'm going to be starting at element 3 and I'm going to be going to 5 exclusive. So this gives me the value of 2 and 3, again using 0 indexing. So I can do it very fast. Now you can probably also see why that we need the extra value in the pointer array, because when I'm doing this summation value, I need the upper bound to sum over. So as you can see, let's see I'm trying to look for all of the values in the fourth column. I go along here, it tells me I'm going to be starting at element 6. And then I'm going to be going up to element 8 exclusive. So what's that going to give me? That is going to give me 1 and 3. And as you can see here, this is why we increase the pointer array and enables us to perform operations over your compressed format of this matrix extremely quickly. So effectively now, we combine all of these approaches and we get BM25s and we get the speed improvements associated with it. What's even better is that the authors of this paper have actually released it as an open source package under an MIT license, and you can install it just via pip with BM25s full if you want to have all of its dependencies, all of the extras there's added on top. This includes some JAX implementation, and then you can use this as simple as follows from the brief little snippet here. All we take is our set of queries, we tokenize these queries, and then we provide them, if your index is already chained, to an instantiated object with this index, and we can retrieve based on them. So very simple to implement. You can try it out today directly on your data and see if you're getting the speed improvements there as well. So that's been an overview of BM25s in more detail, as well as a run through of a modern approach to building a fast and performant search engine. I hope you found this helpful. If you have any questions, feel free to email info@aragoai.com and be happy to discuss them more. Thank you.